Okay, so unit 3 is about dynamics. So kinematics is all about motion of objects. In that particular case, we're just trying to describe the motion of objects. Okay, so we're not into explaining why. So we didn't explain why a projectile will follow that particular path or trajectory. We didn't explain why an object will be moving a straight line unless you try to force it to stop or what. Okay. So now to explain the motion of objects, that is actually in the dynamics part. So when you say dynamics, this is the explanation of the causes of motion. Causes of motion. And we will try to explain why objects behave that way using mainly the 3 Newton's laws. Okay, and an important quantity when we try to talk about dynamics is the quantity force. Force can just be defined as a push or a pull. Okay, and it is considered as an external influence that can change the state of motion of the object. And the SI unit is Newton. So for force, automatically, if we're talking about force, we use that particular uh, unit, which is Newton, or represented by capital N. Okay, and Newton is actually a derived unit. 1 Newton is considered as equivalent to 1 kilogram meters per second squared. So later on, we will try to define the significance of a Newton. Uh, this is not part of your, I mean, I didn't uh, include this one in your note template. However, this can be found in your textbook, okay? I want to include this one because in this particular unit, you'll be encountering these uh, forces, okay? And an integral part of understanding this particular unit is to identify these particular forces, okay? So let's say, for example, for friction. So for friction, usually we use the symbol F sub F. And remember that force is a vector quantity, by the way. So this is a vector quantity. So it has both magnitude and direction. Okay. So friction, by definition, is a contact force. So when you say contact force, that means that the two forces are, well, in contact with one another. Okay. And it acts to oppose the sliding motion between surfaces. Okay. And its direction would be dependent on, well, it's always parallel to the surface, but opposite to the direction of the sliding motion. Okay. So that means that for friction, that means that if you have a surface, so this is your surface, and if you have an object on top, okay, so let's say, for example, the velocity of the object is that way. So it's moving in that direction to the left. Friction in that particular object would be to the right. So this would be FF. Okay, so just to denote that this is a vector quantity, their force must be there. So if you have another drawing, and again, this is your surface, if you can see, that's parallel. So parallel to the surface. So that is the meaning of that one. These two are parallel with this. So parallel lines. Okay. So the friction is always parallel to your surface. Okay. And let's say, for example, that object is now moving to the right. So friction now would be in the opposite direction. So friction would be here. Okay. So what you're gonna do if you want to identify the direction of friction, well, you just try to identify the direction of your motion, the direction of velocity, or the way it is moving. If it's moving to the right, friction would be to the left. If your velocity is to the left, friction is in the other direction. And if you can see here, again, friction is always uh, parallel to the surface. So it's a contact force. That means that they are in contact with one another. So it could be, well, a box or another box, still creating friction there. And for the second one here, normal force. So actually, these are some common forces that you'll be encountering here. So when we say normal force, again, it's a contact force. So that means that the two objects must be in contact. It is the force exerted by a surface on an object. And its direction, take note of the direction also, it's always perpendicular to and away from the surface. So therefore, if I have an object, this is my object here, and it's lying on the surface, the normal force is just going up. So your normal force is just this one here. This is your Fn. Okay, and if you can see, it's always perpendicular. Well, thinking about the surface, that one there. So it's away, always away. So if your surface is here at the bottom, so normal force is upward. And if you reverse, as long as, if you can see here, it's perpendicular. Okay, so make no mistake about that this is perpendicular to and away from the surface. So it's kind of different with your friction, because friction is parallel to the surface. This one is perpendicular. When you say perpendicular, again, it is 90 degrees from your surface. So that particular symbol, this particular symbol means perpendicularity. And spring force, well, not necessarily a common one, but if we're gonna talk about the Hooke's law, we'll be encountering this. So it's a restoring force. Excuse me. It's a restoring force. It's either a push or a pull of a spring that is exerted to an object. So I think everyone have played a spring, right? So if you have a spring at home, you can try it out. If you're gonna stretch it outward, you can feel that the spring is trying to pull you inward. Okay, so its direction is also dependent. It's dependent on the displacement. So displacement means if you're gonna stretch it out, or you try to press it down, because if you're going to press it down, the spring will also try to push back up outward. So try to take note that same thing with friction here. Spring, the direction of the spring is dependent on the displacement in this case. And another common force that you'll be dealing here is tension force. So it is just a force in a string, a rope, or a cable. Okay, and its direction is away from the object and parallel to the string, rope, or cable to the point of attachment. So usually, let's say I have well, this is a object, and then I have the string downward. Then let's say, for example, I have an object being attached here. So if I gonna look at here, there's a tension from there going downward. Okay, so again, the point of attachment is this one here. Let's change it color there. So the force is downward. That would be my Ft. But again, this is looking at this particular point. However, if I'll be looking at the other point, this one here, if I'm looking at the point of view, my reference would be the object itself. The tension is actually in the opposite direction. Okay, so again, this is looking at the object being attached to the string. So Ft is, if you can see, it's parallel and away from the object, okay, from the point of attachment. So that is a tension. And thrust, although this is just a general term, sometimes generally we just call it as applied force. So it's a force that move objects such as rocket planes or in your cars, the engines, or the people that is pushing the car. Sometimes we just call this one generally as force applied. Okay, if it is not very specific, or if it's not friction, if it's not normal force, if it's not tension force, so we just use Fa, or the applied force. And in the same direction as the acceleration of the object, barring any resistive forces. Okay. So again, if you try to push a table, your applied force there is, let's say, wherever the object is moving. Although there's friction there in that particular case, but the acceleration, if you try to push the object, or if you exert a force that is greater than the friction between the two surfaces, it will accelerate in the direction of your applied force. And lastly, this quantity here, the weight. So this is a long distance force. Okay, so this is just the gravitational attraction between two objects. Well, if you're talking about objects here on Earth, so we use the Earth and the object, and its direction is always straight downward towards the center of the Earth. That's why if you have an object and then you're gonna identify the force of gravity is always downward. Okay, so that is your Fg. It's always downward, and any object on Earth is always acted upon by the force of gravity. So later on, I started with this one because later on you'll be doing what you call as free body diagram. Free body diagram is just a diagram that shows all the forces acting on the object. And that is very essential when talking about dynamics, the free body diagram. Are there any questions so far with this one? These are just definitions. I, I, I won't ask you to memorize this, but it's always good to familiarize this one. Because if you mess up in the place in your free body diagram, the different forces acting on the object, well, for sure, your answer would be incorrect. Again, in this particular section, in this particular unit, we'll be talking about forces, net forces. And this is very essential. Although one thing is for sure, we'll be dealing with with gravity. Gravity is always directed downward, and that's already given. Okay, so an object is always acted upon by the force of gravity. Okay, let's now move on to this the note template that you have. Again, the things here, this is just in your text. You can see that one in your text. I would say that the common forces that you'll be dealing here is friction, normal force, tension, the applied force, and FG, force of gravity. So dynamics can be defined as the part of mechanics that study the forces and their effects on object. So force is measured in newtons, and it is a vector quantity. So force unit is newton, and it's a vector quantity. So therefore, it has both magnitude and direction. So you're gonna treat the force as a vector quantity. So when you try to add them or subtract, remember your vector addition and vector subtraction. Okay. So an important thing to note is knowing to write free body diagrams. Okay. So used to organize forces acting on the object. So just identifying the forces acting on the object. Okay. So you will simply, you can represent a particular object by a dot. So you don't have to draw. If you're talking about a person, you can just use a dot, okay? Or a box sometimes, if you want a box, but most commonly, I'm just using, like, if you have an object lying. So for example, what would be the forces acting on this box here, lying on the surface? So if I gonna draw my free body diagram, so I gonna represent my object as a dot. So this is my object. This is my object. So you just have to draw the dot to represent your object and identify the forces. So as I mentioned earlier, this particular object on Earth, well, it should be acted upon by gravity. So Fg is downward. Okay. And I know that it is lying on top, or it is on a surface. So what force is that acts on a particular object that is lying on the surface? Is it not that we call that one as normal force? So there will be normal force. And it is away, if you can see, it's away from the surface. So the surface exerts also a force on the object in this particular case. And we will make an assumption that all the forces are acting on the center of the object. For every force acting on that object, draw a vector arrow. So again, that is just the arrow that we make here. So that. So and also this. So it's just a straight line showing the size and direction of that force. And label. So the label, you can use symbols for this. Just use symbols. Symbols, e.g. So for normal force, if you're talking about normal force, you don't have to write normal force. You can just write Fn, okay? And numbers are not necessarily written there, okay? And the resultant force is the vector connecting the beginning and the end of the arrow. Well, this is just the same thing as when you say resultant force, this is just the sum of all forces acting on the object. And yeah, same thing as before. If we talk about resultant, you just take the sum. But remember that if you take the sum, you need to take note that 10 newtons north plus 20 newtons east is not as simple as adding their magnitude. Okay, so you have to remember that. Again, this is a vector quantity, so therefore you try to treat them as a vector quantity. Okay, so let's take some examples here. This is on writing or drawing the free body diagram. So we want to draw the free body diagram of this object here. So I'm just going to represent my spaceship or the rocket as a dot. So again, this is my rocket. Okay, so you can just use a dot to represent the rocket. And by the look of that, it's just lying and sitting on a launch pad. So it's not moving. Okay, so again, this object here is acted upon by gravity, Fg. And what else? Well, it's lying on top of a surface. There must be what you call normal force. Okay. And since this is not moving, you can assume that the magnitude of the normal force is equivalent to the magnitude of Fg. Okay. Since rocket is not moving, magnitudes of Fn. So again, I'm using the word magnitudes. Magnitudes of Fn is equal to Fg. Okay. So again, I would say that one because again, it doesn't move. It is not moving. So I would say that their magnitude should be the same. Okay. So okay, let's take for example here. This is the same rocket, but now the rocket is moving upward. So the rocket fires its engine and flies upward. So it flies upward. It flies upward. And let's say, for example, this is accelerating upward. Accelerating upward. So if I'm gonna draw again my rocket, the free body diagram of the rocket. So I'm gonna represent the rocket again as just a dot. Well, even though it's flying now, it's still acted upon by Fg, or the force of gravity. There must be weight. And then what makes the rocket flies upward? Well, this is due to the engine of your rocket. So there must be F thrust or applied force with that. And if you can see, this is now longer. This should be longer. So this is your F thrust. Okay. So F thrust is greater than, F thrust is, the magnitude is greater than your Fg. This symbol here just indicates that I'm talking about just the magnitude, okay? The magnitude of the thrust force is bigger than the magnitude of your gravity. Okay, let's take example number 3.
Sorry,
Yes.
teacher.
Yes.
Example 2, I think you need to depend on the time. Because when the rocket starts to fire and when the rocket are in the constant speed,
Yeah, if it's
their
constant,
balance is different. Yeah,
yeah,
the balance
yes.
is actually different.
Yes, that's why I places the word there, accelerating upward.
Yeah.
To
Okay.
just to, yeah, I know that
Yeah.
somehow if the magnitude of your thrust force is equivalent to the gravity, it's no longer accelerating. It's moving
Yeah.
constant velocity.
Yeah.
So let's just say that it's accelerating upward, so that would be
Okay.
bigger. Okay.
Okay, I know.
Okay.
Thanks.
Yeah, you're welcome. So let's take example number 3. Use the free body diagram below to determine the resultant force. Let us just say this particular force, the magnitude of this and this are equivalent. Okay. So if you're gonna add them, is it not that you're just trying to, if you have F1, again, the resultant force is just taking the sum. Taking the sum. And graphically, what you're gonna do is just like, if you have, how would you add F1 plus F2 plus F3? Okay. I'm taking note that F1, F2, and F1 and F2 have the same magnitude. Okay. And F3 is this one here. Sometimes I'll just, well, if you can see here, these are bold letters, because some other books, instead of using the arrows on top, they use bold letters to represent a vector. But that's quite hard to write down here. So I use the arrow notation for vectors. So if you're adding, is it not that that is just, you go up, so F1, but if I gonna add the vector F2, I gonna start drawing it from the tip of my F1 and then downward. Since they have equal magnitude, that means that that just cancels out. And that is, this is F3. So therefore, the resultant is just equivalent to F3. So the resultant is just equal to the magnitude of F3 in this case. Because if you can see, this is canceled out. So the resultant is just the sum. Well, if for example, if we will give some values of this, let's say F1 is 10 newtons, and since they have equal magnitude, this is also 10 newtons. And let's say this is 20 newtons here. So mathematically, remember that when you take the resultant, you can only take the sum of all x values and sum of all y values. Okay, so that means that for the x values, I only have positive 20 newtons. If my to the right is my positive. The y values here is, let's say for example, going up is positive. You'll have positive 10 newtons, then minus or plus the negative of 10 newtons. If you're gonna add that one up, that's 0. So that gives you 0. So therefore the resultant is just equal to 20 newtons. So the resultant is just equal to 20 newtons to the east. It's east, right? Okay. So if you can see here, remember that I cannot add 20 to 10 and 10 because that is on a different component. That is in the y component. So remember that when we do vector addition and vector subtraction, well, specifically in this case, because we're taking the resultant, the sum, we're just taking the sum of all x component and the y component. And if we're creating a right angled triangle, that means that neither of the x or the y are 0. In this case, the x value or the y value is 0. That's why your resultant is just equivalent to the x value. But in the case wherein you're creating a vector that has a particular angle that is lying in both x and y component, that means that non-zero x and non-zero y, yeah, that could be different. We use the Pythagorean theorem then. Okay. So any questions so far? If there's none, can we have a 10-minute break? 10-minute break. Hey, are you there?
Yeah.
Yeah.
So yeah, we will return at 1:30. Okay. Don't go. I mean, don't leave the meeting. Just yeah, you can stretch out. Okay. So see you in 10 minutes. Share. Okay, we're gonna continue our discussion now. Okay, so example number 4 here. Draw the free body diagrams of the pictures below. So forces acting on the sled. So remember that the question is the forces acting on the sled. Your sled is this one. This is your sled. So we want to know the forces acting on the sled. So again, you can represent a particular object with just a dot. So I'm gonna do that one there, a dot. So if I'll be writing forces acting on this one, let's say for example, let's take into account the friction between the ice and the sled. In this case, but for sure, just like before, you always have your FG. Okay, and it's always downward. Well, if the object is excuse me, if the object is moving, so its velocity, let's say for example, it's moving in that direction. Okay, if the object is in the moving to the left, friction would be to the right. So this would be the friction. This is my FF. Again, if you can see, the surface is here, so the frictional force is always parallel to the surface. But I would expect, since I applying a force there in the direction to the left, so it would be moving to the left. And another force that is present here is that it is in contact with the surface, right? And that contact force is what we call the normal force. So we have the normal force that is directed upward. Okay. And then what else? Well, this particular person is trying to, with the use of a string, try pulling in that particular direction. So therefore, you have there a tension force in that direction. Okay, and that is Ft. And remember that since it is the string that is attached to the sled, so therefore the force acting on this object is not necessarily a force exerted by the person directly, but it's actually the force coming from your tension force, and the tension force is directed in that direction. So yeah, I think that would be all the forces acting on the sled. Any question about this one here? Remember that if you're drawing a free body diagram, you're gonna concentrate on a single object. And in this particular case, the question is the sled. The one that is being asked is the sled. So you're talking about this object here. This is your object, the sled. So you're gonna examine the forces acting on that. And again, there would be gravity, there would be friction, there would be normal force, and the tension force. Okay, for the figure at the right here, I think this is Son Goku, right? Or from Dragon Ball.
It's Vegeta.
Oh, Vegeta. Okay. So yeah, so he's trying to push the box, okay, on the wall. So forces on box push against a wall, so that it does not move. Because I think you have noticed this one. If you have a book, if you're gonna push it on the wall, if your force is not enough, the pushing force that you exert, it will slide down. So let's say, for example, in this case, the force that is being exerted, well, said there, it doesn't move, so it stays there. So we can, again, represent the object is the box. So the box is your object. Now I'm gonna examine what are the forces acting on the box. Well, an obvious one is your gravity, because that is directed downward. Okay, there must be gravity, and it is directed towards the center of the Earth. And since Vegeta is pushing it, so there must be a pushing force, and that pushing force is to the left. Okay, so I'm just gonna call that one as FA, the force exerted by Vegeta. What else? What other forces do you think is acting on the box? Because for sure, in that particular sense, this object will be moving, because if you can see, the forces are not balanced. So there must be other forces here.
Friction.
Friction. Okay.
Friction. Yeah,
Uh,
because of gravity, it will goes down,
mhm,
but because it's touched the wall,
mhm.
so the friction will be upward.
Oh, perfect. Okay. Friction must be upward in this case. This is a common mistake by students. Like in this orientation, they try to make the upward force as your normal force. But then again, that's not the case. Because remember that if the force is not, the applied force is not enough, uh, this will slide down. And if you have a sliding motion, remember that friction would be on the opposite direction. Okay, again, you have in contact the box and the wall. So your wall is your surface in this case. And in this particular case, if you're being asked, where is the normal force? Well, normal force would be to the right. Okay, and since this is not moving, we're gonna learn this one in
Yeah,
Newton's.
because the hand is pulled on the box, so because of the press, so the normal will be the opposite of the pressure.
Yes, yes. So remember that normal force is the force exerted by the surface. This is what I mean that you need to familiarize the different forces, because commonly the students will try to write their friction to the right and then their normal force as upward. But then again, we go back to definition of friction and normal force. Well, these are contact forces, and friction is always parallel. In this case, your surface is the wall. So this is your surface, and this is your object. So when you try to draw the different forces, it should be something like that. And this particular symbol just indicate that this must be equal to the magnitude of this, and this should be of equal magnitude with Fn. Okay. So are there any question with this one here? So it takes time to actually familiarize these things. I know that, but this is the first step. You need to know how to draw free body diagrams to be successful with dynamics. Because Newton's law, which is our next discussion, the first law, it's not talking about a single force. It's talking about the sum of all the forces. Okay. So when you take sum, again, that is just the resultant force. You try to add all the forces. So let's try to continue here. First, Newton's law. An object in motion, so in statement, at a constant velocity. So motion at a constant velocity So when you say constant velocity, you know that acceleration is equal to 0, okay? So when you say constant velocity, automatically acceleration is equal to 0. Motion in at a constant velocity or remain at rest unless acted upon on by an unbalanced force. Oops. Unbalanced force. Unbalanced force. So unbalanced force is the sum of all the forces. So when you say unbalanced force, so this is just the sum of all the forces acting on the object. Okay. So sum of all the forces. So it's very important that you're taking the sum. So you're not only talking about a single force here, you're taking the sum. And inertia is actually just defined as the tendency of an object to resist change in motion. Okay. So change in motion, either moving or the object is at rest. So if you have this particular case here, Fa, if this is equal to that, well, if this is moving, velocity is to the right, for example. So in this particular case, this is moving with a constant velocity. Okay. So if this is equal to this, so it should be moving with a constant velocity. Again, acceleration is 0. And on the other one is the object is at rest. So this magnitude should be equivalent to this magnitude. So in this particular case, velocity is 0. V is 0. Well, same thing as the acceleration is 0. Okay. So this is at rest. So when V is equal to 0, the other way of saying that one is that the object is at rest. Okay. So an unbalanced force can change the state of motion of an object. So the state of motion can be at rest. So you can have the object would be at rest. It could be accelerating, or moving with constant velocity. So state of motion. So when you say state of motion, state of motion could be at rest, accelerating, or moving with a constant velocity. So Newton's first law implies that there is no difference between at rest and constant velocity. Okay. And in equation form, this would be given as F net is equal to 0. So mathematically speaking, this is your first law. Okay. So the net force acting on the object is 0. Okay. So the net force acting on the object is 0 if, again, the object is at rest or moving with constant velocity. So automatically, if the object is at rest, the net force or the sum of all the forces acting on that would be equal to 0 to take the sum. So just like in the previous example, you have at rest on the rocket lying on top of the Earth surface, and you have the car moving with a constant velocity. So for both cases, the sum of all the forces is equal to 0. That's why right away, I would say that Fa here, the magnitude are the same, as well as here, the magnitude would be the same. So the magnitude of their forces should be the same. So use Newton's first law to explain why people are injured in car accidents when they do not wear seat belts. Well, without a seat belt, remember that initially, if you're moving at 100 kilometers per hour, your velocity is the same as the velocity of the car. But once the car is being stopped, if you have a barrier, well, if you have a car here, initially moving at, let's say, so you're driving inside the front here. Then you have a, let's say, barrier somewhere here. Okay. If it hits that barrier, okay, if it's at that barrier, the car will stop. But since due to inertia, it's just a property of objects, you will be moving outward. Okay, because of your inertia, you tend to move forward. Okay, and that could be devastating if you hit the windshield, or if you have here another layer of, you'll hit that particular barrier. So that's the reason why you need to actually have your seat belts on, especially in highways. You're moving relatively at great speed. Okay, so let's move on to the second one. So the second Newton's law. Sometimes books call this one as law of force and acceleration. So when an unbalanced force acts on an object, so now there's an unbalanced force. So this tells you that F net, the sum of all the forces, is not equal to 0 in this case. The object will be accelerated in the same direction as the unbalanced force. So your object, if the net force is not equal to 0, again, you have acceleration. So in this case, another way of looking at this one, acceleration is not equal to 0 in this case. This force is the product of mass and acceleration. So if you can see here, we try to get the expression. This sum of all forces is just the same thing as your unbalanced force. Again, that's the net force. And yeah, so using this notation here, summation of all the F, that is just MA. So that's the famous equation, F equals to MA. But make no mistake that sum here, this is not just a single force. Well, it can be a single force, but again, we're taking the sum. So that's why, if you can observe, the drawing of your free body diagram is very important in this case. So summation of all the forces is equal to MA, mass times acceleration. So the unbalanced force is also called the net force or resultant force. Net force is the sum of all the forces acting on the object. So again, you're talking about net forces here. So you're taking the sum, okay? Hopefully you try to familiarize that one, that in this case, that is why instead of just placing there F is equals to MA, it's relatively important to use summation of all the forces, or you can actually use F net is equal to MA. Either way works. So if you use F net, tell you the sum of all the forces and equal to 0. So actually we got the definition of Newton in this case. Again, 1 Newton is just 1 kilogram meters per second squared. So a Newton, therefore, based on the definition of a Newton, it is the force needed to actually move or accelerate a 1 kilogram object by 1 meter per second squared. So a Newton, if you're going to apply 1 Newton of force, okay, if the net force acting on the object is 1 Newton, and that object has a mass of 1 kilogram, you would expect that its acceleration is 1 meter per second squared. So that's the definition of a Newton. Okay, again, sum of the forces, you can get different forms, but you can see net force is equivalent to that. You're taking the sum. So you could have, well, in some cases, you can have one force, but in most cases, you have more than one force. So just remember that. And a force is a vector quantity, and the unit is Newton. So therefore, you have to remember how to add vector quantities in this case. Okay. So force is a vector quantity. Again, we say that it has both magnitude and direction. Okay, it has both magnitude and direction. So make no mistake that it's a vector quantity. So you will be using the direction of this force. So what is the base unit of the second Newton's law? Again, we already discussed this one. 1 Newton is just 1 kilogram meter per second squared, and its definition of a Newton. So a Newton is just the force needed to move a 1 kilogram object by 1 meter per second squared. Okay, let's take this example number 7 here. A 1.00 times 10 to the power of 3 kilogram car accelerates at positive 1.5 meter per second squared. Determine the net applied force. Okay, so let's say, for example, I use the, well, it doesn't specify if it's moving up or to the right. Let's just say the car is moving to the right. So I use to the right as my positive direction in this case. So I'm going to write my given quantities here. Mass is 1.000 times 10 to the power of 3 kilograms. And then the acceleration is positive 1.5 meters per second squared. We want to know the net force, F net. Okay, so the net force could be, again, could be consist of more than one force. But anyway, in this particular question, we're just being asked to get the net force. Okay. So for our solution, well, you have acceleration, you have mass. So you can just use the second Newton's law, MA, and solve for the accelerator or for the F net. Well, you just have to substitute your mass, 0.00 times 10 to the power of 3 multiplied by 1.5. So 1.5 times 1, this would give you an answer of 1.5 times 10 to the power of 3 newtons to the right. So again, if you can see, since net force, this is vector. So even though you're not explicitly being asked to solve for the magnitude and direction, but since the question is the net force, and net force is a vector quantity, so you need to give both magnitude and direction. Okay. So still, in some cases, some of you still don't realize this one. Like velocity. Velocity is a vector quantity, so therefore, the final answer should be given in both magnitude and direction. Okay, so let's take the second example, number 8. A force of 315 newtons to the left, or the direction is left, is applied to a 75 kilogram box. Determine the box acceleration. If the box was originally at rest, what would be its velocity b, or what is velocity b after 2 seconds? So for letter A, the acceleration, well, you're given F net is 350 newtons to the left, okay, and the mass is 75 kilograms, and then A is question mark. However, right away, remember that based on the second Newton's law, whatever the direction of the net force would be the direction of your acceleration also. So therefore, this direction is left. So without necessarily solving it yet, I already know that the direction of my acceleration is left. Again, the reason being is that since the net force is directed left, so the acceleration is also left. So if I'm gonna use my second Newton's law, F net is ma. So A is just F net over m. So F net is 350 newtons, and then A is, mass is 75. So A would be, so this is now the magnitude, and automatically, since I'm using the standard units, or the units, mass is in kilogram and the accelerator, or the net force is in Newton, so automatically the acceleration is also in meters per second squared. So this would be 4.7 meters per second squared. And again, without necessarily having that part of the computation right away, it's to the left because of, again, that's to the left there. So according to second Newton's law, again, the direction of the net force is the same as the direction of the acceleration. So therefore, it also applies. If the direction of the net force is left, so the acceleration is also to the left. So for the second question, this is where your learning, or at least what you ever know in your kinematics, because letter B is a kinematics question. If the box was originally at rest, what would be its velocity after 2 seconds? Well, you would assume that if the net force is constant, this acceleration is also constant. So that means that 4.7 meters per second squared to the left. We're given that. Okay. And it is originally at rest. So initial velocity is 0. And we're given a time of 2.0 seconds. So in this case, you can express this one as negative 4.7 meters per second squared. So to solve, remember that the displacement equation that we use in kinematics, that would be applicable here because this acceleration would be constant. So therefore, we can use, I think one of the equation there would be V is equal to VI plus AT. So in this case, this is 0 plus negative 4.7 times 2. So the velocity after 2 seconds, so that would give me negative 9.4 meters per second. But then again, in terms of direction, 9.4 meters per second, that would be to the left. So the answer is that. So this is the case wherein you, again, letter B is a kinematics problem because velocity is a kinematics quantity. But since acceleration is part of the second Newton's law, you can use that information. Again, if the net force is just constant, which is things that we'll be dealing with, that particular force being exerted on an object is the same all throughout. So we would say that the acceleration is also the same. Okay, let's take this example here, and then after which we'll have a short break. Okay. So you're given the graph between the force and the acceleration. So well, for different cases here, you have straight line A, B, and C. So this is force against acceleration. How can we find the mass? Well, if we're gonna examine that one, that is just a straight line, and the slope of a straight line is delta y over delta x. In this case, though, that y is force. So that means that that is just the delta of F, the force, and this one here, the acceleration, is your delta x. So this is delta A. So if you can see here, is it not that F over A, if we gonna go back to our second Newton's law, so by comparison, second Newton's law tells us that this is MA, and if you're gonna divide F net with A, that gives you the mass. So therefore, the slope of a force against acceleration gives you the mass. Mass of the object is the slope of a force versus acceleration graph. So this is F versus A graph. Okay. So you can recreate this graph by in a certain experiment. Like if you're gonna increase the net force acting on the object, you would expect that the acceleration will also increase, so on and so forth. Okay, any questions? So let's have another 10-minute break, and we're gonna finish the 2 examples, and after which I'm gonna give you your homework for this section. Okay. So Okay, so okay, let's continue our discussion on first and second Newton's law. So I'll be assigning example number 10 and 12 for you to work on today. Excuse me. So, yeah. So example number 9. In a three-way tug of war, teams pull on a rope with the following forces. So you're given F1 as 30 newtons east. Second one is 20 newtons north. And F3 is 15 newtons west. So we need to determine the net force. So we're trying to get the net force of the rope. So net force is just the sum of all the forces. So that means that I'm adding F1 plus F2 and then F3. So F1 plus F2 plus F3. Again, the sum is just the net force. Again, net force is just the sum of all the forces. So graphically, if I gonna show that one, so again, we can represent east is going to the right. So this would be my F1. F2 could be written to the north, that's upward. And west is to the left. So this would be your F3. So F1 therefore, so again, to draw the vectors, you start with your F1 that's going to the right, it's east, that is your F1. F2 is going to the north, and that is your F2. And then F3 is to the west. So to the west, that would be to the left. So it's around 50 newtons. So it should be longer than your F1. So it doesn't have to be very accurate, but it should represent at least the representation. Like in this case, F3 is longer, should be longer than F1 because F1 is only 30 newtons and F3 is 50 newtons. So now, remember that the net force is drawn from the tail of the first vector added. So therefore from here towards the tip. So therefore this is my net force. So this would be my net force. Okay. That should be my net force. And again, this is my net force. This represents my net force. So graphically, I can represent that one, that my net force is lying on the second quadrant, okay? So if you can remember, we used the in solving for the net force, we use the component method. And for the component method, we try to break down each force to its x and y component. Okay. So for F1, automatically y is 0 because you don't have any y component of your F1. It's lying along the x-axis. It's to the right. So therefore, this is positive 30.0 newtons. And then F2. F2, again, we try to break down to its x and y component. It's north. So therefore, that particular, well, if you can also see in my diagram, it's pointing upward. So x is 0 there. Now this is 20.0. 0 newtons. And again, this is positive because upward, again, we use the Cartesian coordinate system, that upward positive and to the right is positive. And then you have F3. F3, therefore, again, you have x and y component. And in this case, your x component is negative 50.0 Newton. And that is negative because it's to the west, so opposite to the direction wherein we set as positive value. And the y is 0. Okay. And the next thing that you're gonna do is you take the sum of all x's and the sum of all the y's. So if you can see here, for the x's you have positive 30, then plus 0, then plus the negative of 50.0 Newton. Okay, so the sum along the x is negative 20 newtons, and summation along y would be, for the first one it's 0 plus positive 20.0 newtons, and then plus 0. So if you're gonna take the sum, that just gives you positive 20.0 newtons. Okay, so that also somehow agree with the drawing that we have, that it should be in the second quadrant. So negative x, if you can see, negative x, positive y, second quadrant. Second quadrant. So therefore, our representation, or at least the drawing that we made here, is somehow closer to the actual. Okay. Although this is just an approximation, but that approximation is relatively close to the real value. Well, after taking the sum, we need to get the magnitude. So the magnitude is just the magnitude of your R, or the resultant force, is just the square root of summation of x squared plus summation of y squared. So that is just the square root of x is negative 20. But if you can see here, regardless of if it's negative or positive, still it should give you an answer, positive value. So if you're gonna take that one, that gives you 28.3. So that's the magnitude. That is still the magnitude. So this is not your final answer. So for the direction, so let's say for example, I'm gonna take again, when you get the direction, you should base it from the tail of your resultant vector. So again, in this case, you're talking about this block line. So let's say for example, your theta is this one here. Okay. So solving for theta would be tangent inverse of, well, the opposite side is your y, the adjacent side is your x, so summation of all the x's. Again, where did I get this one? Well, if you're gonna draw just a line perpendicular to each other, so this is your summation of x, and this would be your summation of so this would be the summation of y. So if you have this triangle here, that triangle there, so opposite is summation of all the y's, and then the adjacent is the summation of all the x's. So solve for that one, that would be tangent inverse of summation of y, 20 over 20. So that should give you an answer of 45 degrees. 0 degrees. So therefore the final answer should be, so the net force would be the combination of your magnitude and direction. So that would be 28.3 newtons, the magnitude, and then 45.0 degrees north of west. So this would be the final answer. And yeah, it's 45 degrees north of west. Or sometimes if it's 45 degrees, you just say north of west. That would be acceptable, or even west of north, because anyway, it's just in the middle between north and west. Okay, so I'm gonna give these two examples here as your homework. And this is due on Tuesday. Okay. So submit it in the Google Classroom. So example number 10 and 11 would be your homework, and you need to submit them on Tuesday. Okay.